Okay, so the last thing that we have to do is we have to be able to prove statements using matrices. And the setup for these is exactly the same, that we are going to do a base case. We are going to show it works for n equals 1. We are going to do an assumption. That means we're going to show it, assume it's true for n equals k. We're going to do an induction. We're going to show it's true for n equals k plus 1. And then we are going to make a concluding statement. Remember that, because proof by induction is always those 4 steps. Let's get started on this one. We want to prove by induction for all natural numbers that this matrix to the power of n is equal to this matrix. So let's start with n equals 1. That would just be 1 minus 1 naught 2 to the power of 1 is the same, is equal to 1 minus 2 to the 1 naught 2 to the 1. Is that true? Yes, because 1 minus 2 would give minus 1. Okay, cool. So we want to assume it's true for n equals k. So that would mean if we had 1 minus 1, 0, 2 to the k, that would be equal to 1, 1 minus 2 to the k, 0, 2 to the k. Cool. And then we need to show it's true for n equals k plus 1. How can we do that? Well, we can take 1 minus 1, 0, 2 to the k plus 1, which is our matrix, and we can split it up into being, I think I'm going to split it up this way around just because how I prefer powers to work, but we're going to split that power of k plus 1 into a power of 1 and a power of k. Now you could have this either way round. You could have the power of k on the left, but I think if I'm going to multiply into it, I prefer my small matrix to be on the left. Just makes more sense in my head. Now the reason that we've done that is obviously that we can take that matrix that's there on the right and we can substitute in for it what we've already assumed. We've assumed this is equal to 1 minus 1, 0, 2 to the k. So let's do that. That would mean this is equal to 1, and then 1 minus 2 to the k, 0 and 2 to the k. And then we could try and expand this, so it might end up being a large matrix. For our top left, remember you times the top row by the first column. That'll be 1 times 1 and 0 times minus 1, so that'll just be 1. For the one below that, it's the second row times the column, so that's 0 times 1 and 2 times 0. That's 0. For the ones on the right hand side, that would give us, so first row times second column, it would give us 1 minus 2 to the k minus 2 to the k. And on the base, we would get 0 times 1 minus 2 to the k, which is 0, and 2 times 2 to the k. Okay, does that look exactly like we want it to look? Well, let's look back at what we're trying to prove here. We are trying to prove this statement, so we would like it to look like 1 minus 2 to the k plus 1, 0, 2 to the k plus 1. So there's going to have to be some manipulation that takes place for us to get that result. What manipulation are we going to do? Well, we're going to use index rules again. So look at what we're trying to prove. We can certainly, obviously the 1 and the 0 are fine. We can collect our terms here. So say this is 2 lots of 2 to the k, and we've also got 2 lots of 2 to the k here. And then we can use the fact that 2 times 2 to the k is the same as 2 to the 1 times 2 to the k, and index rules, they would add together. So we get 1, 0, and then 1 minus 2 to the k plus 1, and 2 to the k plus 1, which we've shown. We should then have our conclusion, which is that the statement is true for n equals 1, and if true for n equals k, that implies true for n equals k plus 1. Therefore, by induction, it's true for all natural numbers. Cool, okay. Second one. I think it's going to be more of the same, don't you? I think you're right. Let's try n equals 1, shall we? So if n equals 1, we've got minus 2, 9, minus 1, 4 to the power of 1. Is that equal to minus 3 plus 1, minus 1, 9, and 3 plus 1? Yes. Okay, we'll assume for n equals k that minus 2, 9, minus 1, 4 to the power of k is equal to minus 3k plus 1 minus k, 9k, 3k plus 1. And we'll show it's true for n equals k plus 1. So again, we're going to use the same general trick, that if we have this matrix to the power of k plus 1, we can split it into this matrix to the power of 1 times this matrix to the power of k. And then we can use the fact that we know about this matrix to the power of k, or at least the fact that we've assumed about this matrix to the power of k, to put it in a form that we want. So we can say, based on our assumption, that this is equal to minus 2 minus 1, 9 minus 1, 4, and then we have minus 3k plus 1, 9k minus k, and 3k plus 1. So we're then going to multiply across, and that will give us, so it times this by minus 2, so that's going to go to 6k minus 2, and then minus 1 times minus k is plus k. So that's our top left. For our top right, we're going to do minus 2 times 9k, so minus 18k plus 27k plus 9 from timesing that by 9. Bottom left, we're going to have 3k minus 1 minus 4k. Bottom right, we're going to have minus 9k plus 12k plus 4. Okay. We should tighten this up a little bit. This would give us overall 7k minus 2, minus k minus 1, 9k plus 9, and 3k plus 4. Now look at what we're trying to show. We're trying to show that this goes 3 lots of k, 3 lots of k plus 1 plus 1, 9 lots of k plus 1. So we want to try and take out factors here of 3, 9, 1, and 3. Did I mess up something there? Yes, I did. So this shouldn't have been k here, should it? No. That should have been minus 9k. And so we end up overall, sorry, there with minus 3k minus 2. Okay, so we want this to take out factors of minus 3, minus 1, 9, and 3. So we can say that we've got minus 3 lots of k plus 1, because that would give us minus 3, and we want to get to minus 2. We've got minus lots of k plus 1. We've got 9 lots of k plus 1. And we've got 3 lots of k plus 1 plus 1. And that is put it in the form that we need. Statement is proved. Conclusion statement. Okay, cool. So that's all that induction is in, well, in further maths actually. It's not just a lower sixth thing, that's in upper sixth as well. And you can see that it's the same process each time. I think that's really crucial to keep it on board, because it allows you to prove tons of things. We just scratched the surface of what it can actually do in these 3 little examples.